So we are summarizing the equations of all the basic laws. The first one is we have seen Faraday's laws of electromagnetic induction in this time varying fields unit starting. In the first case, when the closed loop is stationary and the magnetic field is varying, we have derived one equation in the form of cross products, that is del cross E bar is equal to minus dou B bar by dou T. Already we have derived this expression in our previous class. Just I am summarizing those results, that's all. So what is the Faraday's law in your general differential form? Differential form is del cross E bar is equal to minus dou B by dou T. And what is that Faraday's law in integral form? So this is the basic differential form and this is the integral form. In integral form, how we can express the Faraday's law? Integral E bar dot dl bar is equal to minus dou B by dou T dot ds bar. Okay, so this is the Faraday's law in differential form, that is del cross E bar is equal to minus dou B by dou T, which we should remember very well. So integral E bar dot dl bar is equal to minus dou B by dou T dot ds bar. Now we have also derived in our previous class Ampere circuital law expression, modified form of Ampere circuital law, which is del cross H bar is equal to conduction current density Jc plus displacement current density Jd, which is equal to dou D bar by dou T. So this is the Ampere circuital law in differential form. Now what is the Ampere circuital law in integral form? In integral form we already know integral H bar dot dl bar is equal to enclosed current I. Here in time varying fields, this integral dou D bar by dou T dot ds bar will be also added. All these we have derived in our previous lecture. Now general form of Gauss law, in our first unit we got this del dot D bar is equal to rho v, and integral form is q equal to integral d bar dot ds bar, or that is equal to volume integral of rho v dv. Now for isolated or static magnetic fields, we from our second unit we got the expression del dot B bar is equal to 0 and integral B bar dot ds bar is equal to 0. So these Maxwell's equations next we are going to study. So before this we are summarizing all the laws, the expressions for all the laws, which are for Faraday's law differential form is del cross E bar is equal to minus dou B by dou T, and integral form is integral E bar dot dl bar is equal to minus dou B by dou T dot ds bar. And Ampere circuital law in differential form is del cross H bar equal to J bar plus dou D bar by dou T, and integral form is integral H bar dot dl bar is equal to I plus displacement current density dou D bar by dou T dot ds bar. And Gauss law in differential form is del dot D bar equal to rho v, which we have derived during divergence concept, and its integral form is integral d bar dot ds bar equal to rho v dv. And for static magnetic fields, del dot B bar is equal to 0 and integral B bar dot ds bar is equal to 0. Now these are the expressions for our general 4 laws which we have studied throughout our subject EMF. Now let us express the Maxwell's equations. Maxwell's equations for free space. Free space means there the volume charge density rho v will become equal to 0 and the conductivity sigma will be also 0, because free space is nothing but simply air only. So for that your Maxwell's equations, these general equations will be modified like this. That is, here we are not expressing anything in new manner. This Faraday's law will remain same. Del cross E bar is equal to minus dou B bar by dou T. Okay, and here this integral form will be also same. Integral E bar dot dl bar is equal to minus dou B by dou T dot ds bar. Next, as we are saying that this is present in free space, your second Ampere circuital law will be modified as del cross H bar is equal to this J will become 0, because in free space we know that Jc is equal to sigma E bar, but we are saying that sigma is equal to 0. So this term Jc is avoided here. Jc is avoided, and what is the other term that is left out? That is dou D bar by dou T. And we are saying that rho v is equal to 0. What will happen to this del dot D bar is equal to rho v? Del dot D bar is equal to rho v means del dot D bar is equal to 0. For free space, rho v is equal to 0. And also integral form is integral d bar dot ds bar is equal to 0, because as rho v is equal to 0, this right hand side will become 0. Next, for static magnetic fields, the equations will not change. That is del dot b bar equal to 0 and integral b bar dot ds bar is equal to 0. Okay. So next we are going to deal with the Maxwell's equations for a good conductor. Already we have defined the properties of conductors in third unit. For a good conductor, volume charge density inside that conductor should be equal to 0, and your normal current density, conduction current density J bar, is much greater than dou d bar by dou t. Okay, so just we will leave it as J bar only. Now for these modifications, for a good conductor, how will be the Maxwell's equations modified means, your general Faraday's law will be as it is. Del cross E bar should be equal to minus dou b by dou t. That will be always same, for whether it may be for a free space or a good conductor or in general form. This formula is constant. Del cross E bar is equal to minus dou b by dou t. This equation is always constant, and the integral form of this equation is integral E bar dot dl bar is equal to minus dou b bar by dou t dot ds bar. This is constant. But here for the modification, we are saying that conduction current density Jc is much greater than dou d bar by dou t. So it is enough if we write the normal conduction current density J bar. So your Ampere's law will be modified as second Maxwell's equation, which is del cross H bar is equal to simply J bar. That's all. Okay. And in integral form, we can write it as integral H bar dot dl bar is equal to I, which is equal to integral J bar dot ds bar. This is normal Ampere circuital law, which is valid for a good conductor. Next, for Gauss law, we are saying that del dot d bar is equal to rho v. But for a good conductor, what is the value of rho v? That is equal to 0. So del dot d bar is equal to 0. And in integral form, that integral d bar dot ds bar should be also equal to 0. Now for static magnetic field, anyway del dot b bar is equal to 0 and integral b bar dot ds bar should be equal to 0. So these are the 4 Maxwell's equations. First one is for Faraday's law, second one is Ampere's law, and third one is Gauss law, and fourth one is for static magnetic fields. These are the 4 types of Maxwell's equations. We have discussed Maxwell's equations in general form. Second part is for free space, and this third part is for a good conductor, just small modifications in the equations. So these equations are very important. We should remember them very well. Okay. Thank you.